application of representation learning for semantic search, which is something still useful for the large language model era. So I guess recall that when we talk about representation learning, what we care about is that we want to have a mapping that given a raw input X, which could be an image, it could be a text, it could be some audios or videos, and you want a mapping that say parameterized by theta that maps this into phi theta X, and this is a vector, let's say in dimension m. So every image is mapped to a vector, every sequence of text can be mapped into a vector, so on and so forth. And what you really want is that you want similar images to be mapped to similar embeddings. By the way, this is often called embeddings. Sometimes it's called representation. I think probably because representation is too kind of like generic, people often use embeddings. And sometimes people just call these features. I think we will just use the word embeddings, which is pretty much the most common word right now. So this is the embeddings of this image into the Euclidean space. So basically you embed the image into Euclidean space. So it's a point in the Euclidean space. And often what you want is that you want similar images, or maybe similar text to be mapped to similar embeddings. So for example, if you have like maybe a cat, two different cats, cat 1 and cat 2, and you want this in the Euclidean space, their representation or their embeddings are similar. And if you have an airplane, for example, then you want let me not try to draw any of this, I'll just write it. You probably want the embeddings to be somewhere far away. That's pretty much the idea. So you want similar images to be mapped to similar embeddings. You want different images to be mapped to different embeddings. And then you can use the embeddings to do some similarity search. For example, you can say, I have the embeddings for this image of cat, and I want similar images of cat. I will just go look at which other images have similar embeddings, and those are supposed to be similar images. And the same thing for text and audios and videos. We probably mostly use the image as an example. Later part of the lecture, I'm going to talk a little bit more about text, but the technology are very, very similar. So we'll just start with images, which is the most canonical way to discuss this kind of like ideas. So that's pretty much the basic ideas of embeddings. I guess we have discussed some other applications of embeddings, which are you can use these embeddings as an input to a linear classification, and you add a linear head on top of it. You do a so-called linear probe. Those are useful tools, but these days people don't use those anymore that much because you can just use the end-to-end model as opposed to have these two separate steps. So that's why the most important applications these days for these embeddings or representation learning is this similarity search. Okay, so then next, let's talk about how to train these embeddings, right? This is one of the main tasks for this lecture. For this course, we are trying to teach a little bit about how to train these models. Let's start with images. So for image representation, the way that people do it is the following. You start with, okay, I guess there are two ways. The first way is called supervised pre-training, which is not very common anymore, but because it's very easy to describe and it existed in the literature, we'll talk about very, very briefly. So you can use the supervised pre-training for representations, for embeddings. And the idea is very, very simple. What you do is you just use a neural network. Let's say, suppose you have a neural network X and you have a gigantic neural network. How do you draw it? Like you have like many, many layers. And you use this to predict some labels. You have a supervised classification task. You have 1,000 labels, for example, in ImageNet, and you train a neural network to predict the labels. And this neural network has many layers, right? And often the last but one layer is some kind of like a vector, and then you add some kind of like some matrix W to turn it into logits, to turn it into kind of like maybe this is the logits, and then you do a softmax, right? That's pretty much what often neural networks look like. We discussed this before. So, and you just call this layer the phi theta x. You say the last but one layer, the penultimate layer, is the representations. You just drop everything afterwards. You say, this is my representations. I'm going to use it for my downstream applications. I can use it as inputs for some other classification tasks, which is the linear probe approach, or I can just use this to measure similarities between images. So, right, so that's the so-called supervised pre-training. And you can see, the concern is that you have to use a large label data set to learn this. Especially you have to use a relatively large label data set, because if your labels are only just binary, maybe a missed like a 0 to 10, then presumably the features you learn, the internal representations you learn, but to predict those labels are not diverse enough, right? So suppose the only thing you care about is whether it's a 0 to 9 digits, then you probably only recognize certain kind of like patterns that is only related to the digits, but not other patterns, right? Maybe more extreme example, suppose the only labels you have is like black and white, whether this is like a black and white image or colored image. Then you don't have to have any representations to any kind of complex representations to predict the label very accurately, and then the representations wouldn't be useful for other tasks. However, if you have like a diverse enough label set, maybe like 1,000 labels like in ImageNet, then the representations are generally pretty good. But still, like the limitation is that if you want to scale it, you want to get more and more labels, it's very expensive. You have to get more and more labels, more and more data, use a lot of labelers. So that's why people move towards the unsupervised approach. So this is called contrastive learning. So there are different forms of this, but at least one of the original motivation is that you want to learn these representations without needing any labels from images. And the approach is like this. So there are many details. So the general principle is that you have an image X. You first use augmentation to generate two versions of it. So you say, I guess, I don't have I didn't have the slides, but you can imagine, let's say, suppose you have a X hat and X tilde. These are augmentations. And for those of you who haven't heard of augmentations, it means that you do random crop, random flip, sometimes random blurring, sometimes you add random noise. There are many different ways of doing augmentations. And I think cropping is probably the most important thing. You have a big image, you crop a small part of it. If you Google search quickly, you can see online many visual examples. Because it's random, so you can use two random seeds to generate two augmentations. Maybe you have a big image and you get the X hat is one right top corner and the X tilde is the left bottom corner. And maybe you can add additional flips, blurring, so on and so forth.
For the supervised case, how do we get the ground truth for the labels that they represent embeddings in Euclidean space?
So, can you repeat the question?
Yeah, how do we know the ground truth for the label if they just represent an embedding in Euclidean space? So
I guess you're asking why. I'm trying to translate your sentence a little bit. Like, are you asking why even you are able to predict the ground truth, predict the labels perfectly, right? Even if that's the case, why this representation is good? No, that's not the question.
We have a ground truth representation. Like, where does that come from?
So, I'm trying to see what's the.
Because this label is...
There's no so-called ground truth representation, by the way. So like the representation, if it satisfies certain properties, it's probably a good one, but there's no so-called ground truth ones.
Okay. Because the label is supposed to be a point Euclidean space defining the embedding of some text or image, right?
No, the labels are just discrete labels, like, whether it's a cat or dog or bulldog, so on and so forth. Oh, maybe that's the confusion. Oh, so this is a classification task, just to clarify. This is a very simple vanilla classification task. Like, you have like a foreign class is like I think ImageNet, like maybe bulldog is one class, like some special Persian cat is one class, like a fire truck is another class.
If we just want the word things or by like a n-dimensional embedding, can't we similarly require neural network for
Yeah, what is the deterministic? The question is whether you can use a deterministic method. What are the deterministic methods?
Like just take pixel values and then put it in a vector and then something like averaging. I mean, something like that.
Yeah. So for example, if you just this is already a vector, right? It's already a tensor, like in the beginning, right? Like there are numerical numbers. If you concatenate them, then but you don't have this property that similar cat will have similar embeddings, right? For example, you can have a Persian cat in this position and the other position. In the raw pixel space, they are very far away from each other, right? If you compare the two pixels, pixel by pixel, they are very different. But humans will see they are the same cat. So somehow you have to extract the semantic meanings from it.
And like you talked about how we make sure that the neural network just ensures that, or like this embedding technology ensures that.
Yes, exactly, right. So we're going to try to find embeddings that satisfies this kind of property. And one way to do it is by just doing a classification task. So, and the representations, there's no proof for why the representations are good, but intuitively, if your representations are not capturing the similarity of the images, you probably cannot predict the labels with a linear classification anyways. So that's kind of the, so for example, if you use the X as the representation and you take a linear classifier, you wouldn't be able to predict the labels. Any other questions?
It's like this linear classification, different from fine-tuning, because it's frozen, like the other way.
No. So here we are using this part as your representation. Like, it's not maybe I didn't get the question. Like, so you tune this from scratch first of all.
Yeah.
Yeah. So that's the difference from fine tuning. But sorry, can you repeat the question? Maybe I didn't get it.
No, I think that makes sense because it's being trained from scratch, and then you're saying you're freezing up to that layer, and then applying the linear.
You don't apply the linear transformation, you get rid of it. You just declare this is my final goal.
My final deliverable.
Any other questions about the supervised approach? Okay, great. Okay, so now the unsupervised approach, and recall that our goal is to produce something like this. We don't care about the final classification. The classification is a mean towards the end. And here I don't even have classification labels. I don't have a data set with labels. I just have a bunch of images, nothing else. So I want to find a method that can give me that representation, such that similar images are similar, in the Euclidean space. So, and the approach is like this, you use the X and do augmentations, you get different, two augmentations. Of course, you can have multiple augmentations. You just take two random one, by random cropping, random, flipping, sometimes adding blurry, kind of like make it a little bit blurry, adding Gaussian noise, so on and so forth. Sometimes you do some color transformation. You make it black and white. You make the color seem a little bit different. There's a family of augmentations. Eventually, exactly what augmentations are don't matter that much. You have to have enough diverse augmentations, but that's it. And then you get these two things, and then you say, I want these two. So you can apply a neural network on this, right? You can get phi theta x hat, and you can apply a neural network phi theta, and you get phi theta x tilde, and you say you want these two to be close. So that's something you can express by a loss function. You just say this two needs to be close. I need to minimize the distance between this. Right? So, and you don't need any label so far. Of course, this wouldn't work by itself because you can see, if this is the only objective you have to make these two, embeddings close, then you just map everything to the same point. Right? Every images, no matter their augmentations of anything, you just map to the same point, everything becomes close afterwards. So you need something that counterbalance this thing so that not everything gets mapped to the same point. You need to say something needs to be far away from each other. Otherwise, being close without a relative measure is meaningless, right? You have to say something is close, something is far, right? So then how do you get something, get the counterbalance? Then what you do is you say you have another image. This is a completely different image. Maybe like say, what's the notation I use for this? I guess, I just don't want to mess up my notation. I guess I just have, another image Z, let's say. And Z, again, here I'm applying some augmentation just to make it kind of like more like, tap check in some sense, so that they are in the same augmentation space. Maybe you get z hat, and then you apply this phi theta z hat. You apply the phi theta, the new network, and you get phi theta z hat. And now you say, I'm going to have another part of the objective to try to encourage these to be far away. And maybe these two should be far away as well. So basically, if there are augmentations of different images, they should be far away. And if there are augmentations of the same image, they should be close by. That's pretty much the fundamental objectives, the main objectives you want to design. There are many different ways to design objectives to encourage this kind of like distances. But this is the main gist. And do you see some issues with this? Go ahead. Yeah.
What happens if X and Z are actually similar?
Exactly. That's a great question. Right. Exactly. That's exactly what I was trying to ask. Right. So there's one possible issues with this, which is that if X and Z are maybe, let's say, two Persian cat, they are just different positions, or maybe two similar airplanes, but not the same image, right? So because you don't really know whether they are similar or not, you just take another image. So yes, in that case, your objective here for being far away is counterproductive, right? So for example, if there are two different airplanes, then you should actually make all of this close to each other, right? But your objective is trying to make them far away, right? So in those cases, you are being counterproductive. But the answer is that's fine, because in most of the cases, X and Z are not similar. If you sample two random images from your pool of images, most likely they are not similar to each other in any sense, right? One of them is the airplane, the other is a chair, the other is a building, that's most likely the case. With some small chance they are similar, but you just say those are collateral damage, like you have to kind of like deal with that, right? So basically, by and large, this is the right objective, and it turns out that the benefit of this objective, trying to make them far away overrides the damage it makes. So that's pretty much the answer to this.
How do you learn eventually though that like cats are closer to dogs and airplanes are to dogs?
How you are eventually learn this?
Like, even if you sample X and Z, then you want to be able to learn that X and Z might be more similar to each other than X and Y, right? So how does the model allow for that?
So I think this is I think there's some interpretation of your question requires some deep mathematical study, which I was in. I wrote some papers on this, but maybe let me try to clarify your question. So you are trying to ask what makes so why is surprising for you? Like maybe that's the question. That's my question back to you. Like in what sense it's not explained?
No, it's kind of a follow-up from someone else's question is like the chance that like we have X and Z and that they are similar to each other. Just like how do we this model that we have here, how do we make sure that we can somehow represent that dogs and cats are similar to each other? More similar to each other than say like dogs and airplanes. So
I think okay, let me try to give you a simpler answer, and then if you're not happy with it, I can tell you a deeper answer. So this objective, you try to make these two close, right? You want this to be close by. You want these two embeddings to be close. That's kind of like how you make sure similar things are closer to each other, right? And also, but then you try to deal with the degenerate situation where everything is closed, and then you try to make random things far away from each other. So then the only way that you can enable this is that the similar things are close to each other, and the different things are far away from each other.
The idea is that you want like cats to be less far away from dogs and airplanes.
Right.
Right. So.
Oh no, I don't think that's at least that's not my goal at this moment. I think that you can. So I think for simplicity, let's just say you want cat, you don't really care about cat is further, closer to dog than airplane is to dog. Kite and dog and airplane are just three different type of things. They are all considered to be far away from each other, enough far. You just want different type of cats to be similar to each other. And actually, even if you really look into the data, the closest, suppose you have one cat, I don't know what other breeds of cat but so basically you're only just actually all the nearby points are actually even cats from the same breed. So even cats from different breeds are still quite far away from each other. Of course, eventually I think the points will be organized in some somewhat hierarchical way. So but that's kind of more like a secondary effect. The first order bit is just that maybe cats with the same breed are close to each other. You don't even care about other things.
Everything kind of spaces out equally. And if I have a plane, and all of them would be vectors that just space around the circle because you keep adding more.
I didn't get it.
Sorry, that was a bad question. If everything is just everything you want it to be equally far away, is that what you're saying?
No. Look, no, I want the similar things to be close to each other and different things to be far away from each other.
Okay, think about it.
That's that. Yeah, right. So, I'm not sure whether maybe this is a bad format. So I think maybe let me see whether I can find quickly. How do I do this? So somehow last time.
If I add another Y in there, right?
So maybe one thing that let's try to clarify is that there is a fundamental goal here, and there's also approach so there's a desiderator, which is that you want similar images to be close to each other and different images to be far away from each other, right? That doesn't mean that you put everything just randomly there, right? If you put everything randomly mapped to random points, it wouldn't satisfy this at all. So you do have to organize everything in a very, very nice way, right? So that if you have an airplane, that point, is close to other airplanes, right? And it's close, but it's very far away from other cats. So that's clear. Okay. And you're asking about the approach, right? Okay. So what's the question about approach?
How are we saying that if I add in a Y over there?
Y here? Okay.
Yeah. And so if you have another Y, and then you say okay, Y has to be super far away from X, it has to be super far away from C.
Yes.
That would make them space out evenly. If you just go by what you're saying. Do you kind of see what I'm saying?
Let's say that's true. Yes.
But we don't and back to his. What if the Y is
it's very similar to cat, right? So let's say this is a cat. So and this is like an airplane.
Yeah.
And you are saying you have another Y, which is also a cat, right?
Or maybe a cat looking. Yeah, sure.
Yeah. So but let's say just exactly a cat.
Okay.
Let's say it's exactly a cat, and I think that's what I was trying to explain to that question. So if this is exactly a cat, yes, you are right. The loss function is doing some counterproductive stuff. It's trying to push away the cat to be far away from each other, but that's fine because most of the Y's are not cats, right? If you draw a random Z that is you draw a random pair of X and Z from the image data set, most likely they are very far away from each other. So the hypothetical Y you mentioned is only a very small fraction of the type of data that is there. You just say they make some damage. Yes, the loss function makes some damage. It's not exactly achieving your goal, 100% because if you can really achieve it 100%, then it's so easy in some sense. So, but you just say I don't care because but in some sense, eventually, what happens is that you want the phi of Y to be also, right? So let's say Y is a different cat, right? So you want phi of Y to be far away from this, right? You want it to be far, but you didn't achieve it when you optimize it. So it's in a loss function. It's trying to damage your goal, but it wouldn't succeed because there are other things that are trying to help you, right?
You believe also that there's a lot of labels protection, this is not a data set where you have just images of cats and airplanes, because not this assumption of the chances of getting an X and a Y that are both a cat and go is not to Enroll?
If you don't have diverse enough images.
Yes.
That's true. Yeah, you do have to have diverse enough images. And but
How is that different from the
but you don't need labels, right? You don't need the labels for the images. So diverse enough images is easy. You just download a lot of images from online. Right? Getting the labels is much harder. And in some sense, if you cannot get diverse enough images, that means there's no enough diverse images in this world. Test set is easier as well. Like the diversity is you have to relative. Like suppose somehow in this world there's no diverse enough images, then that's fine because that's my whole universe, right? Right. So in some sense, diverse enough unlabeled images is granted in some sense. It's always the case. Does that answer the question? Okay, cool. Yeah, so yeah, just to repeat, I think it's kind of like you should think of this like multiple different forces that balance each other, right? You want similar images to be close to each other. You want random images to be far away from each other, which is not always the goal, but it eventually everything balances out. Yeah. Okay, so sounds good. So now let's try to write a objective function, a mathematical objective function to encourage some of these pairs to be close and some of the pairs to be far away. Okay, so that's the next step. And the objective here is like this. So what it does is the following. So I think it's called SimClear. So it takes a batch of images. There's some kind of like an efficiency perspective in some sense, as you will see, so that the loss function is probably not the cleanest simple way to express this philosophy or this kind of like a goal in some sense, but for some efficiency perspective, you always do this. So you first sample a batch of images. This is random images. There are some cats, there are some dogs, so on and so forth. And then you say, you build, you augment. So you augment into two type of images, right? Use first the head, the first copy for each of them. And then and you also do the second copy, and I'm organizing it as indices of a matrix. So basically I have these 2B examples. X hat 1 and X tilde 1 are the augmentations of the first image. X hat 2 and X tilde 2 is the augmentation of the second image, so on and so forth. Okay. And now I want to build some kind of like a matrix, if you really think about it, right? So what you really want is that you want this, suppose, this matrix is capturing the similarity. You want here to be big because you want a similarity between this augmentation of the same image to be big, right? And you want augmentation of this and you want this entry to be big because these two are both augmentations of the second image. Right? Maybe these two are two different cats, and then you want the two cats to be similar. And these two are two different airplanes, you want them similar, right? And in any of the other off-diagonal entries, you don't want them to be similar, right? So maybe this entry is a cat versus an airplane, you want it to be as small as possible. So basically, what you do is you say, and you measure the similarity. So the similarity will just be between two images. It's just like you take suppose you have similarity between X and Z, you just say the similarity is the inner product of the embeddings. And often you normalize the embeddings, which makes the inner product is the same as the cosine similarity. So the similarity between X and Z are just the inner product. And if you translate here, this entry will just be the inner product between X hat 1 and X tilde 1. So, and the same thing here, that this entry is the inner product between the embeddings here and the embeddings here. Basically for every ij entry, you see the inner product is just the phi of x hat I and the phi of x tilde j. So in some sense, you fill in the entries here into this matrix, and you want this matrix to have the diagonals to be big and off diagonals to be small. I'm not doing really anything deep. It's just I'm translating it into a slightly different language. Okay, and but how big it is big and how small is small, right? Still haven't specified, right? So the way to exactly say what is big and what is small in this matrix is the following. So you look at it row by row, let's say. So for each row, you want this term to be big, the diagonal term to be big, and the off diagonal term to be small. And the loss function you use for each row, let's say, should I call it row I? The loss is minus log. You take the exponential of let me see whether I'm making some small typos. I think let me use for every column. It doesn't really matter, it's just the notation thing. Like, let's say for every column, you look at one column, you want the diagonal term to be big. So for every column, you take this. This is hat I transpose. I guess maybe I should write transpose here. Transpose phi j. Oh, sorry, this is I. Let me write it down and I will interpret. This is the same term as, and then you have okay, so this is a little bit complicated, but what is this term? This is really, suppose you call this matrix, let's just say temporarily, let's call this matrix each entry is Sij, similarity Sij. So this is exponential Sii, right? This is the I times I, right? So this is the ith entry, so maybe this entry. Right, so that's what, and this is the same thing, exponential Sii. And if you think about this, right, so this term, this function is decreasing in this term. So if this term is big, I think the function is small. So you are minimizing the function. This is a loss function. So let's check that. So I think without this log and this, I think this is an increasing function in the Sii. If Ss is bigger, I think you can verify this increasing function. And then when you have a log, it's still increasing. And when you have negative, it's decreasing. So basically, this loss function is trying to make this term bigger. Okay. So, and, am I right? I think I'm, yes. Okay. And now for these terms, it's in the reverse direction. So, okay. So first I see what are these terms. These are the Sij, right? Because this is j and this is I. So basically, these are all of these off diagonal entries here. And you have a sum of the exponential of them. And you want, if you check the monotonicity, you want these terms to be small so that the whole loss function is small. And if these terms are small, the whole thing is bigger, right? Like the division, because these are in the denominator, so this thing is bigger, and with the log it's still bigger, and with the minus is smaller. So if this term is smaller, then the whole thing is smaller. So basically you are encouraging Sii to be big and Sij to be small, and also the kind of the comparison between them is in this log sum exponential sense. So basically you want them to be, in some sense you want Sii to be comparably bigger than Sij in some sense. So, and in some, this, from this, it sounds a little kind of like complicated, right? You have so many math, but eventually what does this really mean is that you are trying to, at least one interpretation here is that you are trying to distinguish, so another interpretation is that you are trying to distinguish, between which one is the augmentation of the same image. So in some sense, what he's trying to do here is that if I give my x height I, the first copy of the augmentation for i's image, I want to know which of these x tilde is my pair, right? So this is a classification. In some sense, you are just really doing this is the same as a multi-class classification, where you are trying to classify between my pair versus all the pair augmentations of the other images. So this is really classification. You are classifying between x height I, which is the augmentation of the same image, versus all the x height, x tilde I and x tilde j. And your logits, the input to this classification is this similarity number, and you're doing a softmax. This is just literally a softmax, and you take a log, which is the standard kind of like cross entropy loss for this kind of multi-class classification problem. So I think that's, in some sense, that's originally how they come up with this objective. And one small thing here is that this is for column I, right? And you have to sum over all the i's. So for each I, you are doing this classification problem. You are trying to classify which one is my friend, right? Like which one is kind of like from a different image. And you do this for all the columns, you sum them up, and that's your loss for this batch of examples. So for each batch, you have a loss, which is the sum over all of these i's. Maybe let me pause here. This is a little bit complicated.
I'm just trying to understand the minimization here.
Yep.
Minimize the loss here.
Yep.
Sorry,
You are minimizing loss. You are minimizing. There is a minus here as well. You are minimizing the version with the minus.
Yeah. Alright, so to minimize it, I'm just trying to understand what happens to the, how does that, I think you explained it, but can you like how does it make sure that the conditions are met?
Yeah, maybe let's see. So one way to think about this is that, do I have a colored? So if you think of this term as A, and this is A, and this is B, let's say. Okay, so then your loss is minus log A over A plus B. And we can just check the monotonicity of A or B, right? The monotonicity in B is very easy. If B is bigger, then this A over A plus B is smaller. And with the log is still smaller, and with minus is bigger. So it's monotone in B. Right? If B is bigger, the whole thing is bigger. So basically, if you want the loss to be smaller, you want B to be smaller. So for A, I think it's just reverse direction. I think, you can do this if you want 1 minus B over A plus B. This is equal. And then it's decreasing in A. This part is decreasing in A. With the minus, it's increasing in A. And with the log, it's still increasing. With the minus, it becomes decreasing. So this function is decreasing in A. That means that to minimize the function, you should maximize the A. Any other questions?
So if you do all the possible combinations, does the model see a lot more negative examples than positive, in the same? And that's what you want, in the ratio?
Yeah, that's a great question. I think, okay, so maybe that's a great question. So first of all, maybe let's also introduce some notation. I think this, right? The augmentation of the same thing, this is called positive pair. And any other things, any other pairs are negative pairs. So so I think people sometimes call this random pairs. Some people just call this negative pairs. I think from what I see, people are converging to the word negative pairs, even though as we discussed a lot before, they are not always negative. You could have some small chance that they are actually a good positive pairs, but you just treat them as negative pairs. And maybe before answering your question, so actually in practice, people don't have to get these positive pairs necessarily only through augmentations. You can find other ways to find positive pairs. For example, if you have an image, and you can use the image to generate some text. Maybe you generate some text description. And then you can call the original image x hat I, and you can call the text description x tilde I, and you'll say this is a positive pair. That's also allowed. So in that case, basically all the tilde version are texts, and all the hat version is images. And if they share the same index, they are positive pairs. If they don't share the same index, they are negative pairs. And that's actually how you train the text, shared representation between text and images. So you just create this kind of shared kind of like pairs with both image and text, and then you know how to represent both image and text. Okay. So, and now going back to your question, what's if you count the number of positive pairs, it's only in the diagonal. And if you count negative pairs, everything else is negative pairs. So that's true. There are a lot more negative pairs than positive pairs. But I think that's actually pretty reasonable because the negative pairs has much weaker signal in some sense. Like, in many cases, it's actually not that hard to distinguish two images that are very different. So in some sense, you do need more negative pairs to counterbalance the positive pairs to some degree. And another thing is that actually what people in practice really found is that they need a stronger negative pairs, than just the randomly chosen negative pairs. So there is something called, negative mining. Negative pair mining, and sometimes also called hard negatives. You are trying to find hard negatives. And what are the hard negatives? The hard negatives are those cases where they look somewhat similar, but not really exactly. Like, so for example, you could have maybe an image, which is about a kid playing a soccer, and then you have another text which is kind of like about soccer, but there's no kid, right? It's probably FIFA, like the World Cup, something like that. And do you think this text about FIFA World Cup is the same? Should be matched to the kid playing soccer? It's kind of like a little bit kind of ambiguous in some sense, right? So and you call those kind of cases hard negatives. So those are kind of like potentially distracting and pairs in some sense, and you put those in your loss function data distribution you are training on, so that you make the loss more demanding. You say, I cannot, not only I have to distinguish, very clearly kind of like different images or different kind of like, type kind of, data. I have to also distinguish those things that are seemingly similar, but not really. So generally speaking, this is actually one of the biggest trick in practice. You try to find out what are hard enough negatives that are not positives. Because if it's too hard, it actually eventually becomes, the more and more similar they are, eventually they should be considered as positive pairs. So, and it's how to balance that, because anytime you are trying to filter through your data, you find more and more harder negatives, and at some point you cannot tell apart hard negatives and positives. So you have to stop somewhere, so that you don't confuse yourself.
I just out of curiosity, what's the computational complexity of this? Of going through and computing the loss for every single missing intention on every single one in the matrix.
Yeah, so it's B squared, right? So like
right, okay, as long as it is B squared. Okay, yes, it's enough.
So but B squared is actually, that's actually a good question. So B squared is not that of a problem, because the real issue is that how do you compute the embeddings of all of this? So that is actually proportional to 2B. So basically you have to do 2B forward paths to compute the embeddings, right? But each of these embeddings is much more expensive. You have to go through billions of parameters to compute one embedding, right? So that's the real computational bottleneck. Just the getting these loss functions done with B square operation, that's cheap, generally speaking.
You generate this if you want to have more data augmentations for each image you see.
Oh, so you just use random augmentation.
Augmentations and random.
You do a random augmentation. So if you want to have more augmentations, you just go through the data multiple times. Each time you generate some different augmentations. Yeah. But actually, you never really go through the data more than a few times, I think. But you use a random augmentation so that each time you are applying different tactics or different combination of the tactics in the augmentation.
So if you were to find negative pairs, would you not put all of the pairs in? Like you would only put like some subset of the other data points?
If you have very good negative pairs, then what would you do?
Yeah.
Sorry. So what you are proposing to do?
Like, would you then not use all of the negative samples, but only some subsets? You'd have like the one positive and then some, like fewer?
Yeah, exactly. Right. So if you have better negative pairs, you should just replace this whole thing by positive pairs and a set of like strong negative pairs, hard negative pairs. Yes.
To make
the loss more demanding. Yes. Yeah. And yeah, exactly. So for example, by the way, another thing is that, what I didn't say, clearly here is that this B is not the whole data set. This B is only a subsample version of the data set. So B could be 128, maybe 1,000, 4,000, so on and so forth. And what you do is that each time you take B of the real examples from images and you build this matrix, and then next time you move on to another B examples. And how you select that B examples also matters a little bit. So first of all, you shouldn't select those examples that are very okay. I guess we are getting into deep situations, like some of the practical situations. In practice, you have actually many data sets, right? You maybe have an image data set, you have a data set that are always about buildings, you have an image data set which is from the web. You may have like different data sources. So, and presumably, those images in the same data sources are somewhat more similar to each other. So, and when you sample these images, first of all, people always sample these B images from the same source so that they are somewhat similar to each other. And that's one way to create harder negatives, right? Because if they're all very different, then it's just so easy to fit this loss function. You just clearly tell. For another example, I think, I was involved in a startup which is doing some of these things with natural languages. And with there's natural languages, they are, for example, for coding, there are different programming languages, right? Java, C++, so on and so forth, right? So if all of these examples are from different programming languages, so it's so easy to tell apart them. Like your loss function is naturally so small, and there's nothing you need to do with it. So that's why you probably should pick these B examples from at least the same programming languages, or maybe even the same code base on the same repo, so on and so forth, to make it a bit harder to distinguish. So basically, the trick is that you need to start with, things that are somewhat difficult to distinguish to make the loss function more demanding, and then you can learn a stronger representation. Any other questions? Okay, so I think, wait, anything else I didn't say? Okay, and for languages, oftentimes you don't have augmentations. So, and what people do is that, the public papers, had many different other ways to prepare the positive pairs. So if you're just training these embeddings on languages, then you, for example, sometimes use X tilde as so you have a document, and the tilde version, the first augmentation, so-called augmentation, is maybe the title and the headers, and the second copy is probably just the raw text. So then you create a pair. The pair is the title versus the headers versus the raw text, and that's positive pair. And then if you have the title one document and raw text of another document, that's a negative pair. Obviously, it's less likely for them to match to each other. Yeah. Okay. So now let's briefly talk about, how do you use this in the semantic search. So I think you can probably imagine it's very simple. So in semantic search, the goal is that you are given a query and you want to find all similar kind of like objects in your pool of, say, documents or images. For example, you have a large collection of images and you are given one image, a new image, you want to find all the similar images in that pool. In the text, I think, you have a query and you have a large a collection of documents and you want to find which document is most relevant to the query, maybe answering a question in the query, so on and so forth. So it's always something like you have a collection of, say, documents or objects you care about, and you have a query, and this is a query, and you want to find among this collection of documents which one is closest to the query or collection of images. And the way you do it is that you just, very simple. You just given the embedding models or the representation, the phi, you just compute phi of d1 up to phi of dn in advance. And then given the query, so at the test time, you have a query, you take the query and you map it to the embedding of the query. And then among these embeddings, these points, right, you have a bunch of points, you want to find the nearest neighbor of this. You just find, you want to minimize, you want to find the ID, say I, such that I guess let's maximize the inner product. Let's maximize the inner product between phi theta q and phi theta di. So how do you maximize this? The simplest way is just you go over all the i's. You don't have to recompute the phi because phi is all the embeddings are already stored. You don't have to rerun your neural network. You just have a bunch of vectors, and then you take the inner product of all of these vectors with this guy, and you look at all of the numbers and you see which one is biggest, or maybe which one is the top 10. You don't have to always get the biggest. So that's the brute force way. And if you want to make it faster, then there are this kind of like a tool called vector database, which is, or maybe so there's so basically there are other kind of k-nearest neighbor algorithms. The k-nearest neighbor algorithm means like it's exactly solving this problem. So you're having a lot of points, and the k-nearest neighbor algorithm will find the k-nearest neighbor, the k closest neighbors in the cloud, in the point cloud. I think there it's a purely algorithmic question. So I guess we won't. It's not actually much of interest for this course. It's just purely algorithmically, how do you find from a large collection of vectors, how do you find the closest vectors? And practically speaking, you can use a vector database. A vector database is actually designed for this. The database is storing this and then enabling how do you take the max with the inner product. Okay, so, and now finally, I think we can also talk about, let's see, what else we should talk about. Let me see how much time I have. So I think, finally, I think we can talk about some of the applications of semantic search. You can see semantic search is useful by itself because you just have to do search in some sense, right? In many cases. And actually most of the search system these days, except some of the legacy system like, Google, I think Google is also using semantic search to some degree, but we don't know exactly. It's kind of like a more fusion of many, many methods. But most of the new methods, if you implement a semantic search system yourself, you probably should use this kind of ideas. And there's one more application beyond semantic search in the large language model area, which is you use this in this so-called retrieval augmented generation. Retrieval and the motivation is that once the large language model came out, they are often off the shelf just a generic large language model, right? So they are developed by some of these frontier labs, and they don't see the proprietary information of another enterprise, right? So because those informations, they cannot be leaked to the training data of the frontier labs. But, these enterprises, or even just yourself, like if imagine you want to have some kind of like a personal, assistant, and you have some information that you are not comfortable with sending to, the frontier labs for training. And then you have to somehow let the models to ingest this additional information, the proprietary information in some form, at the test time, right? And how do you ingest this additional information to the large language model? There are several different ways. One way is you fine tune. You fine tune on your own data, starting from the base model. Oftentimes that's the issue with that is that, that's actually, a good idea for some applications, but, in some other cases, it's just too expensive, right? You only have like a small data set and you don't want to host kind of like a billion, trillion parameter models on your, GPU, or maybe just pay for the cost to fine tune and host those models. So a simpler approach is this so-called retrieval augment generation approach. And what it does is that, it's very simple. You just so basically you have a query, and you have a corpus. Let's say you have a lot of documents, on your, laptop, or you have a lot of documents in the enterprise which are proprietary. And you say, at task time, you do this retrieval. So you first do retrieval to get some relevant documents from your corpus, right? So like maybe you get some of your own, maybe your bank statement, like your other information on your laptop, or maybe in the enterprise they can get the CEO's memo, all of those. And so this retrieval step is exactly something like this, and you get some relevant documents. And then you send a subset of relevant documents, which often is probably 5 documents, 10 documents to a large language model. And then you give them in the context of the large language model. Basically, you just send this to the large language model, and then the large language model will also see the query and also the documents together, and then generate the answer. So this way, you don't have to modify the large language model's internal state. You don't have to change the parameters. You are just giving the large language model additional information in the chat interface in some sense. Like, we haven't talked too much about the context, all of those, but you can imagine you just send this information to the large language model as an augmentation of the generation. So this has, of course, there are trade-offs for different ways to ingesting, the different ways of ingesting proprietary information. The nice thing about this is that it's very modularized, because this is a retrieval thing which is almost completely separated from the large language model. And you can deal with many kind of like data governance very easily. For example, you can say, some users don't see this document, right? Some users don't have permissions to see the earning projection in the company, right, in advance. So then you just forbid those people to have the retrieval, to see those information in the retrieval phase, and then they wouldn't see those additional data. And it's easy to delete information, because you just delete your information from your corpus, then it will be never retrieved at all. So it's easier to forget. And also it's kind of somewhat cheap, because, the retrieval step is always cheaper, much cheaper. So in contrast, for example, if you fine-tune a large language model on all the data in the enterprise, then to delete it, it's actually not that easy. Like, how do you forget about something by unfine-tune it? It's actually still a very open question. But here, this is a very clean way to deal with it. Yeah, anything else? Maybe another thing is that, speaking about the most frontier approach, I think these days, Anthropic, they are actually using a different type of like search algorithms, for this, phase. So they don't necessarily do all the semantical search. What they do is that, they just use, the regular expression matching. So they use large language models to generate some regular expression. To search for certain kind of keywords, but the regular expression can be very complicated. You can probably have, I don't know exactly, because, you cannot really see all the, what, the frontier models always do, because they are hidden in some sense. But I think the common understanding seems to be that you generate a lot of regular expressions to search for various kind of like variants of the keywords. You try to search for all kind of patterns, and then you search relevant documents this way. And this works pretty well for code, partly because the code structure, the repos for code is often much more structured, right? You can, doing regular expression search can give you a lot of mileage to already. You have the very structured file tree, and you have a very strict kind of like keywords for all the variables in some sense, right? The function names, all of those. So that makes a little bit easier to use regular expression. So, but semantic retrieval, I think, are still, at least so far, they are still very useful for many other cases, where this kind of like a regular expression based approach is a little harder to deal with. Or maybe you should do the both of the combination of them, so on and so forth. So basically, I think this retrieval augmented generation is pretty clear that this is very much needed, but how do you exactly do the retrieval, still, depends on your applications. And we don't know exactly which one is the best way yet. Okay, I think, I don't have anything to say that is, that can be done in 10 minutes. So maybe we'll just, stop here, for today.